Hey guys, Spencer here. This is going to be the second part to how to utilize cross-validation in relation to all of our machine learning models. We're going to be utilizing even further methods in terms of how to improve root mean squared errors and R-squared values, or explanation of variances. We're also going to have a comparison in terms of what model is performing better using the same type of data and the same, similar methods. So without further ado, let's get down to it. If you haven't checked out the previous video, part 1, please do so before you go to this video, partly because we have a lot of code that has been written and it'll just be sort of confusing at this point. So I really do encourage you to check out the prior videos that I've created. They are linked down into the description. But anyways, assuming that you have checked out the videos prior, let us now figure out how to create a more robust model with elastic net regression. So let's call this elastic net cross-validation _1. We're going to be using the same parameters essentially. We're going to be using nedv tilde this, and then the same data train. We're going to be using the same method, glm nets, and we are going to be using the same train control values, which is set to train parameters. So one of the things that we will change here is to add an interaction term, and that is done via a caret squared. So think of, we have A, B, and C features. The caret will be A plus B plus C plus A times B plus A times C plus B times C. So that is essentially what the interaction term is going to be. It's like an additive effect to the overall model. We can do this because elastic net regression is a form of regularization. So pretty much not really how many observations or features that we include in our model. There will always be a penalization factor or multicollinearity factor that this particular model will address, and it will slice out the fat essentially. So in theory, we can technically add as many features on top of our overall model, and we might have a better outcome, we might not. But in terms of use cases, you can definitely do this, and it'll make sense theoretically and applied. So that's one of the values we can do. Another value that I want to include is a tune length, and I'll set this to 10. So the tune length is a form of hypertuning in terms of finding different alpha values and lambda values associated with that. So from a range of 0 to 1, it'll go from 0.1 to 0.2, 0.3, 0.4, all the way up to 1, and it'll have different search values with that related lambda value. So let's actually run this so we can have a great visual. It'll take a little bit more time since our tuning length is a little bit longer, as well as the model complexity. And we have some missing values. Warning message, that I don't think we need to worry about that. Yes, we don't. Sweet. So this is what I was saying in terms of a different lambda value and also a different alpha value. We have 0.1, 0.2, all the way up to 1. We have various search values related to our lambda, and that outputs a specific root mean squared error and your R-squared value. It also has your mean absolute error, but we won't really go much into detail on that. In general, the root mean squared error is widely accepted as a final result, and the lower it is, the more robust your model might be. And our best model is related to 0.1 and a lambda value of 0.2120098. 0.1, 0.1, so it's this one. This is our best model. So let us take a closer look into what we have going on. So let's start saving some of these values. Let's do the R-squared value of our elastic net CV_1. Let's save that. It was, I believe it was this value, the R-squared. So 0.8 So notice that this was already tremendously better in terms of what we had going on here. Our R-squared values 0.65, and our prior ElasticNet CV was like 0.72, but this was 0.83. That's just magnitudes better. So adding this particular feature that we have over here, it explained the variance so much more. So let's save that, our R-squared value. One of the really neat things about Caret is that we can call our models, or like our final models, and essentially obtain the coefficients or the individual lambda values that are associated with this. So we can do this. ElasticNet CV1, we call this best tune, and we can call our alpha value or our lambda value. So we can get our lambda, which is that. We can also get our alpha value, which looks something like this. So 0.1, so we can easily map that out. We can create a helper function that sort of just sorts all this out and gets like one particular row. But in this video, I'm just not going to do that. What else can we do? Yes, we can find the best model coefficients, and we can do this by utilizing the coef function. We can just call our ElasticNet CV_1. We will be calling the final model. We also will call the ElasticNet CV_1, and we can call best tune. We can do lambda. So this is our model. So these are all of our coefficients with its corresponding interaction terms. In this case, these are being multiplied with each other, but these are the coefficients for all of our terms within our given model with our intercept. The points are considered to be like nulled out or zeroed. They're not relevant to the overall model. And we can utilize this and save this however we want, and we can even calculate how to predict with this particular model with new incoming data. We'll be doing that a little bit later down this road. In fact, we'll do it right now. Predictions. Sweet. So let's do this. ElasticNet CV1, call this pred. This will be pointing to the predict function. It's a function within Caret. Also, I think it's built in. But all you really need to do is pass in your model, ElasticNet CV_1, and you just need to pass in your data test. And that's it. Our data test is only right here, 88 observations. We should have 88 prediction values. Let's do a length of here. Length. We have 88 predictions. So we are good to go. Let's calculate the RMSE of this. So RMSE, ElasticNet CV_1. Yeah, and let's do RMSE, which is now a built-in function with Caret. We don't really need to write it out ourselves anymore, thank goodness. But ElasticNet CV_1, and we can call the data test. That's what we want. medv. Non-binary. Yes. This needs to be pred. There we go. And then the root mean squared error of our new data is 3.017. This is very, very good. This is like terrific. Holy crap. Alright, so once we have this, let us actually get our related values with our previous model for 0. So let's do the exact same thing. Best model coefficients. And then we can just diagram everything out for model 0. So coefficient, this is ElasticNet CV_0, final model, ElasticNet CV_0, best tune, lambda, we have that. So we have all of our coefficients related to our initial model in the previous video. Once we have our coefficients, we can save that, do whatever we want with it. But let us do the predictions for model 0. And that'll be ElasticNet CV_0 pred. And then predict ElasticNet. There's two E's. ElasticNet initial. And then we put in the same data test. We have our predictions. Now let's calculate the RMSE, elastic net, CV underscore 1, and RMSE, elastic net, CV. Oh, did I not run this? It should be elastic. Oh, I spelled that. Oh, I spelled this wrong. Elastic net CV 0. There we go. And then do this, do that, and then we just pass in our data test with our medv. So we'll just calculate the root mean squared error. Let's calculate that. Set that to 0, and then we have that RMSE. Where is it? RMSE up here. Let me expand this a little bit. 4.2, 3.017. There we go. And then C bind. So as we can see, there's a dramatic improvement in terms of performance overall. The root mean squared error values that we have given over here, it dramatically decreases. Also note that the R-squared value dramatically increases. The more robust our model is, that is related to however many interactions that we have, in addition to finding out what is maybe our best tuning parameter length. Alright, this is the end of my video on how to use cross-validation with machine learning algorithms. In this case, it was elastic net regression, but you can definitely apply this to whatever other type of machine learning algorithm that you may be doing. It's pretty much the exact same methodology and also the same logic, same theory. So I hope that you enjoyed this video. Thank you for watching. Please make sure to like and subscribe, and I'll see you in the next one. Thank you.